Welcome to the Road to Validation Part 1, SOLIDWORKS Flow Simulation. This is the first part in a three-part series that we're running here at Hockridge Systems for the month of May, focused on sort of a detailed start-to-finish design validation process and where some of the different validation products fit into that cycle and what maybe a typical design environment might look like if you were using some of these tools. What we're going to start with today is looking at this question of which tool, particularly from an analysis perspective, is the right one to use at different stages of the process from day 1 to day 100. You probably are aware that Hockridge Systems is one of the largest SOLIDWORKS providers and engineering solution specialists in the United States and all of North America. And so we offer a variety of not only design tools and other software, but also validation tools, mostly consisting of the SOLIDWORKS simulation tools like SOLIDWORKS Simulation and Flow Simulation, but also Simuli Abacus, which is a family of more specialized validation products. And so to help better explain where some of those things fit into a more complicated process, we're going to do this three-part webinar series to try to explain in a little more detail what it would look like if you were trying to maybe answer some different engineering design questions and which tools would fit into that process and how they might work together. So what we're going to use as a subject is this situation of the alternative fuel industry refueling process, where we've basically got some hydrogen fueling trucks that are delivering fuel to a station that, of course, then would need to be able to fit into a variety of vehicles that would fill those up with clean burning hydrogen, which hopefully would be produced from some sort of renewable means. And so we're going to look at, again, if we were going from start to finish through all of these design questions, where would we need to go to answer some of those things and get the type of validation that we need? And of course, if we're talking about software validation and being able to predict the real world impact of certain design changes or what kind of performance characteristics they would have, we're talking about the simulation family of solutions that we offer at Hockridge. That includes not only the products that I just mentioned, but a variety of services and consulting as well that we can provide. Some of you may be aware, of course, that we've got a lot of content posted on our website, our blog, the YouTube channel, and of course, any of you who have used our technical support hopefully have experienced how comprehensive that is. But in addition to that, we provide training and implementation flight plans and consulting, and so we have a pretty good amount of experience on not just what these tools can do, but the best way to use them in a process like this. And we're going to try to show you an example of that knowledge in the next few weeks. So as a case study, we're looking at this hydrogen fueling nozzle adapter. This is kind of that sort of bluish part that you see on the right there is sort of one out of many adapter nozzles that we might need to design to fit onto this fueling filler neck that, of course, needs to adapt it for different kinds of vehicles or different kinds of refueling stations. And so I might want to answer, first of all, if I was on a design project like this, what kind of nozzle shape is ideal? What aspects of that nozzle shape might cause issues with the filling pattern in the flow of the hydrogen gas? And if I'm using this fueling nozzle for, let's say, a minute to fuel up a vehicle or refuel a tank, what are the temperatures going to look like? Do I need to be concerned about something getting too hot or too cold, whether that's just because of what it'll do to the gas or other safety concerns? And so to answer those types of questions, which might be kind of the first thing that drives the overall design, I might want to use a CFD tool, computational fluid dynamics tool, like SOLIDWORKS Flow Simulation. So in the family of simulation products that we offer, SOLIDWORKS Flow Simulation is the one that we typically recommend to do any kind of fluid flow or heat transfer analysis, which operates directly on your SOLIDWORKS models, directly from inside the SOLIDWORKS interface. And this is basically what we would call a general purpose CFD tool, where you can essentially try to predict those types of performance or those impacts without needing any kind of CFD expertise or specialization, or more importantly, needing to make a special version of your model or export it to another interface just to check those things. So SOLIDWORKS Flow Simulation lets you get that kind of feedback directly inside SOLIDWORKS, and some of the technology in that tool makes it much more convenient than it has been in the past to do CFD, so that if you, for example, go make a design change to your 3D model and you want to see the result of that change, what that impact is very quickly, this is the ideal tool for doing that. We like to call that this concept of concurrent engineering, right? Validating the design as you go along and using that information to make trade study decisions and make sure that you're guiding the path of the design properly, not just doing analysis at the very end to find out, what happens after you've already made these decisions. So because we can simulate fluid flow analysis and heat transfer at the same time, this is going to be the perfect tool to answer this kind of first round of questions that we've got. So again, for this case study, what I'm going to be doing here is setting up an internal fluid simulation that includes heat transfer. And I'm going to need to do what's called a transient or time-dependent simulation to see what happens after I'm opening this nozzle up and filling for a minute. I want to see what the temperatures do over time. And all the other results like velocity. And I'll see if I noticed anything that could be improved about the design. So let's jump over to SOLIDWORKS and we'll take a look at how you would set that up in Flow Simulation, and then we'll come review what we've found out. So here I am in SOLIDWORKS 2018. This is the current version of SOLIDWORKS. And I'm going to open up this assembly that I've created, this fuel filler assembly. And you can see that right now, this assembly is definitely designed to be as machined. It's the detailed mechanical drawing. I've got my fasteners in there. Of course, I've got a nice silicone rubber seal in the middle there. Of course, I need to make sure I'm preventing any hydrogen leaks from getting out, which means I can't have this at too high a pressure, that kind of thing. And while there probably would be some structural or other kind of stress concerns later on with, for example, the seal, right now I'm just going to try to make sure that I have the basic nozzle design right first, since that's probably most dependent on this kind of fluid flow conditions. Once I've got that general shape down, maybe later on I can examine some strength properties. So if I wanted to see what the hydrogen looks like if it's flowing through this nozzle, first thing I got to do is just turn on my SOLIDWORKS Flow Simulation add-in by clicking the button right there from the SOLIDWORKS Add-ins tab. And so the SOLIDWORKS Flow Simulation is going to run the analysis using the solid bodies, solid geometry that's already in my SOLIDWORKS assembly. The only decision I typically have to make in a situation like this is if I want to run an internal analysis or an external analysis, or both. So for example, in this case, if I wanted to, I could simulate not only the hydrogen flowing inside this nozzle, but the air around the outside, or even simulate the hydrogen flowing out the end of the nozzle to see what would happen if it were just go into a big empty tank. For right now, I'm really just concerned about what the effect of those internal kind of bend radii and other factors are. So I'm going to do an internal analysis here to focus in on that, and that'll make sure it runs in a more reasonable amount of time. And so to do an internal analysis, there's really just one required step, which is to close off the openings in your SOLIDWORKS model. That way, SOLIDWORKS Flow Simulation will be able to detect where that internal cavity is, and also it'll give us something to click on to put in our boundary conditions, like, for example, the flow rate we want to assume. And so I could model those kind of closing bodies myself if I wanted to, but also if I go to the Flow Simulation tab, we have a special tool called Create Lids, which will do that for us. So I simply have to click here and then click on the flat face where any of these openings would be, like, for example, the inlet there and then the connection at the back. And those lids will be automatically created, and that will seal up the fluid volume. And so if I switch over to this other configuration that I've already made, where those lids are already in there, you can see that. And if I wanted to confirm that I had done this properly, you can see here that if I unhide that lid, it's definitely there at the inlet nozzle. I can go to the Check Geometry tool on my Flow Simulation tab in the Command Manager. And I can click this button called Show Fluid Volume to see in 3D in the graphics area where that empty fluid space is being detected. And as long as it looks like it's in that bluish color there, that means that Flow Simulation has successfully detected the cavity. It tells you what the volume is of that empty space as well. And you're good to go for the analysis. So there's no need to model up special geometry to represent where your fluids are or to assign those materials to them. It's detected as long as you've got a sealed internal cavity. So that means at this point I can create my analysis and start putting in all of my setup conditions. And typically it's easier to see kind of what we're talking about here and how we want to define some of these conditions if we do a section view. So let me turn that on. You can see again, as I mentioned before, I've got this connection point at the back where it would thread onto a delivery line, and then I've got a gasket with some bolts through it that are attaching this nozzle that I'm designing. So I'm going to use the wizard interface to create a new simulation. This is kind of an all-inclusive interface that pops up here and make sure you define the most important setup conditions for any project that you want to create. First of all, of course, we just have to give it a name here, and I usually recommend giving it some sort of condition name, like for example, 1 minute max fuel rate or something like that. And so we'll do this first analysis of the baseline design right here, which would be the default CFD configuration. And as I click next, I can go through the different screens in this wizard, and the next one would be to specify my unit system. I can use any of the standard ones like SI or US, American units, and I can customize this as well for whatever might be typical in my industry. For example, pressure, instead of PSI, maybe I measure stuff in millimeters of water, I could switch to that. Or maybe my fill rate is going to be in gallons per minute, so I could go down to volume flow rate and change that. That'll make sure all of my input conditions as well as any of the output results will be in a familiar format. So I can click next again, and at the third screen, this is the analysis type window, I can choose the different kinds of physics that will be present in my analysis. We already made that decision of internal versus external, and we can confirm that with the little radio button there in the top left. But now I also may need to turn on some different physics. One of the important things in this analysis is going to be to figure out what kind of temperatures I'm dealing with in both the hydrogen gas as well as this nozzle apparatus, right? If it's getting too cold, for example, that might be dangerous. And more importantly, if, for example, it's not getting heated up or cooled down evenly, that could cause some thermal expansion issues. Maybe it could be a rupture or even just a leak in that seal, for example. And so if I turn on heat conduction in solids, I'll be able to calculate those temperatures in the solid parts and see what that effect is. I could also include radiation if I wanted to, although radiative heat transfer probably is not going to be a big factor here. We're not going to be dealing with super high temperatures. I could also turn on gravity and some other effects for different kinds of problems, but the one that's going to be important in this scenario is time dependency. Since I mentioned that this is going to be a transient simulation because I want to find out what happens after 1 minute of fueling, I could turn that on, put in my analysis time of 60 seconds, and then optionally I could choose how often I want to save out the full result files. So that's what that output time step would do. For right now, I'm going to leave the output time step at 0, which means I'll only get results at the end of the 60 seconds. And that's actually fine with me because there's going to be a different way where I can track certain select parameters over time, and that will take up less disk space and also just be easier to see kind of in a fluid animation or numerical plot. So we'll leave that at 60 seconds, and then click next. And as I mentioned, this is going to be a hydrogen fueling nozzle. And so if I go into my gases folder, you can see that, of course, we have air and carbon dioxide and some of the other more familiar gases, but we also have things like hydrocarbons and some of the noble gases and elemental gases like hydrogen. So I can simply double click that and hydrogen will get added to my project list. And that's going to be the default fluid inside this nozzle. Just so you're aware, if I wanted to, I could add multiple fluids into the simulation and either mix them or, for example, have them in different spaces. Like I could have air around the outside of the nozzle and hydrogen on the inside if I was interested in, let's say, the natural convection airflow patterns. The other thing that's neat about the fluid models in SOLIDWORKS Flow Simulation is that these are an ideal gas model, but they automatically include all of the temperature curves for the different properties. For example, if I go here and browse to hydrogen, you'll see under item properties, the dynamic viscosity, thermal conductivity, etc., are not just single values, but they have a table. And that means that whatever temperature conditions I put in, for example, if I'm flowing this hydrogen into the tank at a low temperature, Flow Simulation will automatically know the right fluid properties to use at that temperature. I won't have to create a special model of the fluid just because I'm in a different condition. So hydrogen is selected, we'll click next. I also need to pick a default solid material. And a good practice here is, since I've got some lids and I don't want those lids to conduct any heat away because that would be unrealistic and it would affect my temperatures, I'm going to make the default material an insulator. That way it won't change any of the heat transfer characteristics. And after the wizard's done, I'll be able to put in the other material properties. I can also put in some wall conditions. You can see that the default outer wall thermal condition is adiabatic. That means that it would be treated as insulated by default. But I know that there would be some air around this nozzle, just the outside air at the filling station, for example. And so I might want to account for how much heat that air pulls away. And so I could change this to another condition. I could either put in some sort of heat transfer coefficient, if I know what that is, or a simpler assumption like just an outer wall temperature or heat generation rate. Heat transfer coefficient is a good way, pretty realistically, to mimic how much heat that outer air would pull away. So I can put in a value like 0.5, and also what that external air temperature is. And this value just represents kind of how fast the air is flowing and how turbulent it is and that kind of thing. Of course, you can also put in your ambient conditions here. I'm just going to stick with standard sea level temperature and pressure for now, although I could change that, and it would make it easy for me to compare the operation of this thing in different environments if that was a concern. And so now that my wizard is finished, I've got a new flow simulation project that's been created. And at this point, I can go in and specify the other materials and the other boundary conditions and run my analysis. So first of all, if I wanted to put some materials in, I can select the solid material drop down here and do things like, for example, select my nozzle and the filler adapter. If those were, let's say, aluminum, I could simply go to the predefined materials list. Under alloys, I've got aluminum 5052, and I can select that. Just so you're aware, if I wanted to, I could also import the materials from the SOLIDWORKS feature tree if I had already designated those. But otherwise, you can select them from the flow simulation library here, which does have more detailed temperature-dependent properties, just like the hydrogen. I've also got a rubber gasket in there, so I could go down to my solid materials folder again. And in this case, I'm using flow simulation with something called the HVAC module, which has an expanded materials library. And that allows me to select this silicone material. And I can simply apply that to the gasket. Of course, I've got some bolts in here too, so I might want to put some sort of steel on those. And again, that's another material available in the predefined library. We'll go with stainless steel 321. So these will all have the necessary thermal properties for my analysis. And at this point, then, I need to put in the boundary conditions to describe how the hydrogen would flow through here. So I can go to my boundary condition menu in the dropdown. And I probably know what kind of volume flow rate I'm going to be getting through this nozzle from the delivery storage tank. So I could click at the inlet down there, which is where that lid is that I've been that I've created earlier, and I can define an inlet volume flow rate. For example, in this case, 200 gallons per minute. One of the other nice things about flow simulation is that with a few simple buttons there, it makes it easy to change the realistic nature of an inlet condition, like if you wanted to add swirl or assume that the flow was coming in at some other vector. I'm going to assume in this case that the hydrogen is just coming in kind of normal to that inlet joint, where we probably would. But since it was probably connected to a delivery line there and it's been flowing down for some length, instead of uniform velocity, I could check this box called fully developed flow. And that tells the simulation that the hydrogen will probably already have a nice turbulent boundary layer and a parabolic velocity profile, all of those traits that would be associated with flowing down a long tube or channel. And so that way I don't have to look up what kind of velocity profile I would want to input manually, or even include that part in the assembly. I can just check that box and it'll be very similar in realism. I also want to change some of these thermodynamic parameters. This is hydrogen, so of course the colder it is, the denser it is, and even though it's not going to be cryogenic hydrogen, which would be way more expensive, I might want to pump this in at, let's say, minus 20 degrees. That way it'll have at least a somewhat lower density than at like room temperature. So I can click OK, and I just want to make sure I select the lid face down there. That's going to force my hydrogen in at that opening, and of course it's going to exit the nozzle at the other end, where I can apply a different boundary condition. And in this case, I'm going to use something called a pressure opening. Since I don't know what the velocity or flow rate or other conditions would be at this end, instead I can just input what the pressure is going to be inside the tank, for example. And that way flow simulation will calculate for me what the pressure gradients and other velocity properties look like at this. Now there are a few key results that I might want to track, and I can do that with something called the goals plots, and that was basically allow me to specify sensors for the most interesting results, and it makes it easier for me to track those. I can do things like a global goal if I wanted to find out, for example, what the maximum velocity was. I could simply go and check the appropriate box for that. I could also check things at an outlet with something called a surface goal, where I could click that outlet face, and I might want to check, for example, how much swirl is there in the flow. So I could check the box for circumferential velocity. Or maybe I want to find out what the average temperature is. And all of these different parameters are available, and you can measure the minimum, maximum, average, or other properties. So those will be automatically tracked for me over time. And the one other setup change that I want to make is in an effort to speed up the calculation time. By default, flow simulation would automatically determine what we call a time step to figure out how many steps it needs to solve this simulation accurately. But there's another option we can turn on under the calculation control options, and that's called nested iterations. If I go to the solving tab, there's a checkbox for it right here. And if I check this next nested iterations box, what that'll let me do is switch to a manual time step instead, while still ensuring that the accuracy is maintained within each step. So basically, I can force my simulation to use a fewer number of steps. If, for example, I have a simulation of 60 seconds, maybe I want 50 steps, well, I could just type in divided by 50, and that'll give me a time step of 1.2 seconds. So that way, all of my result plots will have a nice smooth animation with 50 frames in it, 50 different time points. And the nested iterations will make sure that it does the additional calculations within each of those time steps to make sure that the results are still accurate. So at this point, I could run my simulation. It would use the default mesh if I didn't change anything, although, of course, I have the option to go into my global mesh settings and do that. The default mesh is going to look like that, where it's a sort of Cartesian XYZ grid. And the mesh will automatically refine itself by splitting those rectangular cells that you see in order to capture the geometry more accurately. But of course, if I wanted to, I could change things like the slider to use a more refined starting grid and more refined mesh levels. And also, if I wanted to, I could put in a gap size option here. If I had, for example, any smaller fins or orifices somewhere in this model, I could type in the diameter of that and make sure that the mesher captures those small passageways. In this case, I think the default will be fine though. I will leave this at level 4, and that's still going to solve in a pretty short amount of time just because the geometry is pretty simple here. So we'll go ahead and run the simulation. This is going to automatically generate the mesh and run the calculation at the same time. And it's going to solve pretty quickly thanks to the low cell count here because the geometry is pretty simple and because of those nested iterations that I enabled. And what you're seeing here in the solver window as it pops up are those goals that I created. I'm seeing how they're progressing over time. And this is a good way, first of all, to make sure that I'm kind of in the ballpark in my simulation, that somewhere close to the results I expected, and also to see kind of not only the sort of transient history here, but also if after 1 minute things are sort of leveling off or if they're still changing a bunch. In this case, it looks like the temperature and velocity and everything else is more or less kind of leveled off, which means I'm pretty close to the steady state behavior after that 1 minute. But in the real world, I probably at this point would then turn off the flow, and that would, for example, stop the velocity completely, if I shut a nozzle, for example, and that would probably make the temperatures change pretty rapidly too. So now that I've completed the simulation, I can go look at these goals and other visual results to see what happens and get maybe some input on what kind of design change I might want to make. For example, I could look at a cut plot, which is basically like a section view that will allow me to see any kind of parameter I want on a plane inside the model. For example, I could look at pressure, and the pressure is fairly uniform and fairly low in this example. We don't want too much pressure because the hydrogen would probably leak out through that seal. Or I could look at, for example, velocity. You can see that I do have a pretty significant velocity gradient. It looks like it speeds up a little bit as I get close to that inlet nozzle, and you can see the boundary layer as well near that threaded connection point. And I can overlay things like the mesh to see where that refinement happens automatically, and also things like the streamlines if I want to see where there might be recirculation or flow separation from the walls of the nozzle. And this can be dragged back and forth through the computational domain to see that effect at different areas. And this is just a great way qualitatively to figure out if you want to adjust the size or shape of anything just for a better streamline pattern. You could also look at those types of results on the faces of the model with a surface plot. For example, here we're looking at relative pressure. You can see that sort of slight gradient there. And everyone's favorite, we can look at the flow trajectories, which would be the three-dimensional paths of the airflow, or in this case, the hydrogen, as it passes through the geometry. We can pick an inlet or outlet point and type in a certain number of streamlines that we want to see. In this case, I've got 60. And then I can color them with whatever kind of result I want. So here we can have, for example, flat arrows showing velocity. And so this animation, of course, is another great way to visualize just qualitatively what kind of change I might want to make. And also I could use this to figure out, for example, if what kind of design change would be more effective at, let's say, reducing some of that swirl that I see. So let's think about that for a moment. If I saw something like that in my flow simulation results, some sort of swirl, and I wanted to try to remove or reduce that, I could make a change to my model. And of course, that would be pretty easy to do if I'm inside SOLIDWORks. In this case, it would be as simple as maybe adding an extrude or maybe patterning it around. Of course, I could do anything else like change the dimensions of the nozzle, the sizes, thicknesses, etc. But in this case, that's the best idea I had. And so I can make that change, and usually the best way to do that is to make another configuration of the part with that change in it. And then I can use something called clone project to copy my flow simulation that I just created into this new version, and that way I can compare them side by side. So if I go back into SOLIDWORKS here, I can switch over to this other revision that I've made. And of course, what I would do is, in this case, clone the project, which I've already done. You could right click on the project and just click clone, and it asks you to give it a new name. And so now you can see that I've got that new variation in there with these flow straighteners. And since all of the setup conditions are the same, I don't have to do anything except hit run. So there's no need to redo the setup or change any of the conditions. And at this point, I could simply load up the results that I ran earlier. And I could check those results that I had before, all the same plots that I had generated on this new design variation. For example, I could look at those flow trajectories and see what happened. And it looks like, in this case, especially if I look at temperature, probably did have some sort of an effect there. There's a little bit of kind of a change in that angle right where it comes into the nozzle at first, right past the seal. But if I wanted more of a hard numerical conclusion, what I could also do is use the compare tool to look at some of these things side by side. And that will take advantage of the goals that I created earlier. So in the results menu here, I can click compare. I can choose the different configurations of my simulation that I ran, and then choose to show the goals and the cut plot and any of the other results that I've generated, and look at them side by side. So when my goal populates here, for example, I can see that the maximum velocity didn't change too much, but the circumferential velocity, the swirl, looks like it changed more. That went down by about 10% or so, which might be significant. And also, interestingly, it looks like those straighteners changed the temperature. Hydrogen was going out of the nozzle at about -3-4 degrees, and that flow straightener apparently looks like it made it, because it's not mixing as well, it made the temperature go up a little bit. And of course, that temperature is because the outside air is 70 degrees Fahrenheit, not the cold hydrogen that's flowing in. And in addition to just seeing this comparison side by side, I might want to also look at those goals in more detail over time. For example, I could look here and plot these goals not only in a table, but I could look at them historically, see, for example, that the velocity is in fact increasing. So it takes 30-40 seconds for it to get close to the maximum flow rate. And also the temperature drops real rapidly at first and then kind of more slowly approaches that end result of about 1 degree. But more interestingly than this, I can actually see these results visually over time as well. If I go back and turn on one of my result plots, like for example the cut plot, and take advantage of something called the Transient Explorer. Let's go back here and turn on my cut plot. This is of course the result at the end of the simulation. You can see the cross section here with the temperature in the outer walls as well as in that internal flow straightener. And what I could do is just right click and turn on this Transient Explorer option. And then by clicking play, I'll be able to see a transient animation of those temperatures and velocities changing over time. You can see that the velocity settles in pretty quickly, but then gradually the outer wall temperatures start to come down. And that might be where I need to start thinking about those thermal expansion effects that might occur inside the seal or inside the housing. So the bottom line is that we are able to run not only a useful comparison and see what kind of impact a design change like this might have, before we actually go start prototyping or spending time and money on tooling. But I can also get a more realistic, transient analysis with some pretty high-end capabilities without needing, a more complex external CFD tool. So because of things like the nested iterations and the more accurate fluid models with temperature-dependent properties in them, We can make sure that our simulations are fairly realistic, even though they're very easy to set up and work with on our SOLIDWORKS model. So some of the capabilities in this tool remove those sort of trade-offs that you may have had to make before. You don't have to compromise accuracy just because you want something that's easy to use. So interestingly, at this point, I think we've seen that maybe this design change would have some benefits from a flow or heat transfer standpoint. And that's just one of the many applications you might use flow simulation for. Of course, it's used by our current customers in a pretty wide variety of industries, everything from electronics cooling to industrial equipment, transportation, aerodynamics, etc. And there are a pretty large community of users of this product, which we can, of course, provide more information to you on if you were interested. One of which is a company called Center Rock that's pretty famous for that Chilean mining disaster that they participated in the rescue of. But what we hopefully can convey to you is that not only do we have a pretty high amount of knowledge of what these tools can do at Hockridge Systems, but in particular with flow simulation and SOLIDWORKS simulation, we've worked with many customers in many different applications for these things. And we have a pretty good experience in not just how to use the tool, but maybe what the right process is, what the right order of the things to look at is. And more importantly, how that could fit into your current process. At what point might you want to do simulation? What kind of questions could it help you answer? What would be the most efficient way to answer, for example, a thermal question like what we just looked at, and then maybe use that information to drive the next stage of the process that might be more of a structural concern, let's say. And that's what we were trying to show you with these this three-part webinar series in the month of May. We just looked at some of the capabilities of SOLIDWORKS Flow Simulation. And so what we might want to look at the next step here is, are those temperature gradients that we found going to cause some structural issues or not? And so we will, in part 2 of our Road to Validation series, which is going to be next Wednesday, we will look at structural and fatigue analysis using some of the information that we found at this first stage of the process. So this is going to be an integrated presentation where we really want to show you not only at what point you might want to use some of these different tools, but how they work together, how they build off of each other, and how they can make for a much more streamlined design and validation process. So again, please make sure to look out for the webinar registration link, which is going to be on the Hockridge Systems website. Go to hockridgesys.com and then go to company events. And you'll be able to register for these next 2 webinars there. Next week is going to be SOLIDWORKS Simulation, which is going to be part 2 of this series, hosted by Silvio Perez, one of the other product managers for SOLIDWORKS. And then finally, the Simuli Abacus portion on May 30th, where we'll look at what types of simulation would require a more advanced real-world multi-physics type analysis with Simuli Abacus, and maybe something that you would do at the end of a design process as a final validation before you go to manufacturing. So again, stick around for those the next 2 weeks if you can, and hopefully you'll see how this all ties together. With that being said, thanks for your time. If there are any questions, I'm going to stick around and try to answer those. Feel free to let me know if you have any questions about what flow simulation can do or how it would work for your design or project. Otherwise, feel free to reach out to support or your local account manager, of course. And feel free to email me as well, DamonT@hockridgesys.com. Thanks again.